In 1916, a British engineer drew a simple curve on paper that would save thousands of lives. 25 years later, America copied it, made it better, and lost the one thing that made it work. This is the story of how industrial efficiency killed battlefield genius. Winter descended on the Western Front in 1916 like an executioner's blade, slow and merciless. Across the churned wasteland of Belgium and France, 500,000 British soldiers huddled in trenches that had become open graves. The mud wasn't just inconvenient, it was a living thing, swallowing men whole, collapsing dugouts, turning every step into a battle against the earth itself. Above ground, German artillery hammered the landscape with methodical precision, reducing wooden barracks to splinters and canvas tents to shredded rags within minutes. The British Army faced a crisis that couldn't be solved with bravery or tactics. They needed shelter. Not just any shelter, but structures that could be erected under fire, transported through impossible supply lines, and survive the apocalyptic violence of modern warfare. Traditional construction was a fantasy. Skilled carpenters were dying in the trenches faster than they could be replaced. Timber convoys choked roads needed for ammunition and food. A proper wooden barracks required a week of labor by experienced builders, and the Western Front didn't offer weeks. It barely offered hours. The solutions attempted were desperate and inadequate. Canvas tents provided no protection from shrapnel that screamed through the air like horizontal rain. Wooden huts, when they could be built, burned like torches when hit by incendiary shells. Dugouts carved into trench walls flooded with every rain or collapsed under near-miss explosions, burying men alive. The mathematics were brutal. The British needed over 100,000 shelters, and they needed them yesterday. Into this impossible equation walked Major Peter Norman Nissen of the Royal Engineers. Born in New York to Danish-Norwegian parents but raised in Canada, Nissen was a mining engineer by training, a profession that taught men to think about pressure, weight, and the geometry of survival underground. He had spent years designing tunnel supports in mines where a miscalculation meant being crushed by thousands of tons of rock. Mining engineers understood something that architects often forgot. Resistance isn't about mass or thickness, it's about shape. In January 1916, at a Royal Engineers experimental station near Ypres, Nissen sat at a drafting table and sketched something absurdly simple, a half circle, not an arch with supporting walls, not a pointed Gothic curve, not an ellipse, a pure semicircle, like someone had taken a cylinder and sliced it lengthwise. The structure would be made from corrugated iron sheets, the same material used for industrial roofing, bent into this curved form and bolted together. No complex joints, no elaborate framework, no skilled carpentry required. The insight came from his mining day. Deep underground, curved tunnel supports distributed the crushing weight of earth evenly along their length. There were no corners where stress concentrated, no flat surfaces where pressure built up catastrophically. The curve was self-supporting through pure geometry. Nissen looked at the artillery-ravaged landscape and realized the same principle applied. A blast wave from an explosion was just pressure moving through air instead of earth, and pressure, whether from rock or explosives, flowed around curves like water around a stone. The first prototype went up in March 1916. 16 feet wide at the base, rising to a peak of 6 feet at the center, just tall enough for a man to stand upright down the middle. The structure used corrugated steel sheets, each one thin enough that 2 men could carry it, but the corrugations themselves, those parallel waves pressed into the metal, gave the material surprising rigidity. It was the same principle that made cardboard boxes strong despite being made of paper. The waves created structural depth without adding weight. 6 soldiers assembled the first Nissen hut in 4 hours using nothing but wrenches and bolts. No welding, no concrete foundation, no specialized tools. The curved steel sheets overlapped like fish scales, each one bolted to wooden ribs that formed the semicircular frame. The ends were closed with wooden panels that could be fitted with the entire structure could be disassembled, transported in pieces, and re-erected elsewhere. It was architecture reduced to its most fundamental equation: shelter equals curve plus steel. The real test came 3 days after completion. A German 150mm howitzer shell landed 40 yards from the prototype Nissen hut. The explosion was catastrophic. A crater 8 feet deep, a blast wave that flattened everything within 30 yards. A wooden barracks adjacent to the test site disintegrated in splinters. The Nissen hut shuddered, flexed visibly, and stood. Engineers inspecting it afterward found the structure completely intact. Some bolts had loosened from the vibration, but not a single panel had failed. The curve had done exactly what Nissen predicted. The blast wave had struck the rounded surface and flowed around it, dissipating into the air instead of smashing through. The British Army ordered immediate mass production. By the end of 1916, factories across Britain were stamping out corrugated steel panels by the thousands. The Nissen hut's specifications were deliberately simple to enable rapid manufacturing. 16 feet wide, various lengths from 10 to 60 feet depending on need, all using the same curved panels and standardized bolts. The genius was in the restraint. Nissen didn't try to make a perfect building. He made a perfect solution to a specific problem. What made the Nissen hut truly revolutionary wasn't just the curve. It was understanding why the curve worked. The semicircular cross-section created what engineers call a compression structure. When force pressed down on the top, the curve translated that vertical force into horizontal thrust along the entire arch. Every point on the curve supported every other point. There was no single weak spot, no critical joint where failure would cascade through the entire structure. The building was, in essence, one continuous piece, despite being assembled from dozens of panels. The corrugated steel contributed a second layer of genius. Those parallel waves weren't just for rigidity, they were shock absorbers. When a blast wave hit the structure, the corrugations could compress slightly, absorbing energy like a spring. The thin gauge of the steel, 22 gauge, about the thickness of a modern car body panel, was actually an advantage. Thicker steel would have been more rigid, unable to flex. The Nissen hut's steel was thin enough to bend without breaking, to absorb impact and return to its original shape. Engineers who studied surviving structures after bombardments noted something remarkable. The huts appeared to breathe during explosions, expanding slightly and then contracting, like a chest inhaling and exhaling. The overlapping panel design added a third survival mechanism. Because each steel sheet overlapped its neighbor by several inches, the structure could shift and settle without losing integrity. Bolts could loosen, panels could slide fractionally, and the building remained standing. This was the opposite of rigid construction, where every joint had to maintain perfect alignment, or the entire structure failed. The Nissen hut was designed to be imperfect, to accommodate damage, to survive through flexibility rather than strength. By the end of World War I in 1918, over 100,000 Nissen huts had been manufactured and deployed. They appeared on every front where British forces fought. In France and Belgium, they housed troops within artillery range of German guns. In Mesopotamia, modern-day Iraq, they endured temperatures exceeding 120 degrees Fahrenheit, the steel expanding and contracting daily without structural failure. In East Africa, they survived tropical humidity that rotted wooden structures within months. On the home front in Britain, they served as emergency hospitals, ammunition storage, and aircraft hangars. Soldiers gave them affectionate nicknames: tin turtles, steel igloos, elephant huts. War diaries and letters home repeatedly mentioned them. One British corporal wrote in 1917, "Jerry dropped a 5.9 not 20 yards from our hut last night. Thought we were done for. The whole thing shook like a drum. But when the dust cleared, there she stood, not a rivet out of place. Slept sound as babies the rest of the night." Another account from a medical officer described a Nissen hut field hospital that survived 3 days of sustained shelling. The noise inside was hellish, like being inside a bell while it's rung, but the structure never failed. We treated wounded throughout the bombardment. The versatility proved as important as the durability. Because the design was so simple, it could be adapted for almost any purpose. Remove the internal wooden ribs and you had an aircraft hangar. Add insulation and a stove, and you had winter quarters. Partition the interior, and you had offices or storage. Stack ammunition crates inside, and you had a blast-resistant magazine. The Nissen hut wasn't a building. It was a platform that could be configured for whatever the military needed. When the war ended, thousands of Nissen huts were sold as surplus. Farmers bought them for storage barns. Families converted them into homes during the post-war housing shortage. Small businesses used them as workshops and warehouses. And here's where the design's true genius revealed itself. Many of those structures are still standing today, over a century later. Across the British countryside, you can find Nissen huts from World War I still in daily use. Their corrugated steel weathered but intact. Their curves still perfect. They have outlasted the war they were built for, outlasted the soldiers who assembled them, outlasted countless permanent buildings constructed with more expensive materials and sophisticated technique. The reason for this longevity lies in that deceptively simple curve. Water runs off it naturally. No flat surfaces to collect moisture and rust. Snow slides off in winter. Wind flows around it rather than catching on corners and eaves. The structure has no complex joints to fail, no hidden spaces where rot can begin. It is, in engineering terms, an optimal form, the shape that nature itself favors for structures that must endure. The mathematics behind the curve deserve deeper examination. A semicircular arch is what structural engineers call a funicular structure, meaning the shape naturally follows the path that forces want to take through the material. When you load a semicircular arch uniformly, the resulting compression forces flow smoothly along the curve without creating bending moments or shear stresses. This is why Roman aqueducts, built 2,000 years ago using nothing but stacked stone, still stand today. The arch shape does the work, not the material strength. Nissen understood this intuitively from his mining experience. In underground tunnels, semicircular supports resist the crushing pressure of overlying rock not by being thick or strong, but by being the right shape. The rock's weight presses down. The arch translates that vertical force into horizontal thrust at the base, and the entire structure remains in pure compression, the most efficient way for materials to carry loads. No tension, no bending, no complex stress states that cause failure. Just simple, elegant compression flowing through the curve. When a blast wave from an explosion strikes a flat wall, the pressure acts perpendicular to the surface, creating maximum force. The wall must resist this force through its own strength and mass. If the pressure exceeds the wall's capacity, it fails catastrophically. The wall collapses inward or explodes outward depending on the blast direction. This is why conventional buildings near explosions often lose entire walls while the rest of the structure remains standing. When that same blast wave strikes a curved surface, the geometry changes everything. The pressure still acts perpendicular to the surface at each point, but because the surface is curved, perpendicular means different directions at different locations. At the top of a Nissen hut, the blast pressure pushes straight down. Halfway up the curve, it pushes at an angle. Near the base, it pushes almost horizontally. The result is that the blast wave's energy is redirected along the curve rather than absorbed by it. The pressure flows around the structure, like water flowing around a boulder in a stream. This principle explains why Nissen huts could survive near-miss explosions that destroyed rectangular buildings. The blast wave that flattened a wooden barracks by hitting it broadside would strike a Nissen hut and slide off, dissipating into the air. The curved structure didn't have to be stronger than the rectangular one. It just had to be the right shape to redirect force rather than resist it. The flexibility of the thin steel added another survival mechanism that seems counterintuitive. Engineers typically think of rigidity as strength. The stiffer something is, the stronger it must be. But under blast loading, rigidity can be a liability. When a shock wave hits a rigid structure, the structure must absorb all that energy through deformation or failure. There's no middle ground. Either the structure is strong enough to resist without damage, or it fails catastrophically. A flexible structure, by contrast, can absorb energy by deforming elastically, bending without breaking, then returning to its original shape. The Nissen hut's 22-gauge steel was thin enough to flex under blast pressure. The corrugations acted like springs, compressing and expanding to dissipate energy. Witnesses reported seeing Nissen huts visibly ripple during nearby explosions, the steel sheets flexing in waves that traveled around the structure. This wasn't structural failure. It was the design working exactly as intended, absorbing energy through controlled deformation rather than rigid resistance. Modern blast engineering recognizes this principle. Structures designed to survive explosions often incorporate flexible elements specifically to absorb shock energy. The Nissen hut, designed in 1916 through intuition and field experience, anticipated engineering principles that wouldn't be formally understood until decades later. 23 years after the Nissen hut's debut, the world went to war again. On December 7, 1941, Japanese aircraft attacked Pearl Harbor, and the United States found itself facing the same logistical nightmare that had confronted Britain in 1916, but on a vastly larger scale. The American military needed to build bases across two oceans simultaneously, from the frozen Aleutian Islands of Alaska to the tropical atolls of the South Pacific, from Iceland to North Africa. The numbers were staggering. Thousands of airfields, hundreds of naval bases, countless supply depots and hospitals. Traditional construction was impossible. The military needed prefabricated structures that could be mass-produced, shipped anywhere, and assembled by non-specialists. The U.S. Navy's Bureau of Yards and Docks studied existing designs and quickly focused on the British Nissen hut. The concept was proven, the engineering sound, the track record impressive. But American military planners saw room for improvement. The Nissen hut, for all its battlefield success, was a product of artisanal engineering. Designed by one man, refined through field experience, manufactured in relatively small batches. America in 1941 was the world's industrial superpower, home to assembly lines that had revolutionized manufacturing. Surely, American engineers could take Nissen's good idea and make it better through industrial optimization. In early 1941, months before Pearl Harbor, the Navy contracted with the George A. Fuller Company to develop an American version of the Nissen hut. The project was based at Quonset Point Naval Air Station in Rhode Island and the resulting structure took its name from that location, the Quonset hut. The first production models rolled out in June 1941, and by the war's end in 1946, American factories had produced over 170,000 units, nearly double the total Nissen hut production from World War I. The Quonset hut looked similar to its British predecessor at first glance. Both were semicircular steel structures. Both could be assembled quickly by small crews. Both were designed for rapid deployment. But the similarities were superficial. Underneath, the American redesign had altered nearly every aspect of the original engineering. The changes seemed logical from an industrial production standpoint. The Nissen hut's continuous curve required custom-bent steel sheets, which were difficult to standardize across different manufacturers. The Quonset hut used flat steel panels, standard 4-foot by 8-foot sheets that could be produced on any industrial press in America. These panels were then bolted or welded to prefabricated arch segments that formed the semicircular shape. Instead of one continuous curve, the Quonset hut was built from multiple arch sections joined together. American engineers also improved the steel gauge. The Nissen hut used 22-gauge steel, which seemed thin and flimsy to engineers accustomed to American construction standards. The Quonset hut used heavier 20-gauge steel, which was perceived as more durable and substantial. The structure also incorporated an integrated wooden floor, plywood sheets attached directly to the steel frame, whereas the Nissen hut had used a separate floor that could be adapted to local terrain. The Quonset hut came in multiple standardized sizes, 16 feet wide like the original Nissen, but also 20-foot and 40-foot widths for larger applications. Everything was modular, interchangeable, designed for maximum production efficiency. A factory in Pennsylvania could manufacture arch segments that would fit perfectly with panels made in California. The entire system was optimized for America's industrial strengths, standardization, mass production, and logistical coordination. On paper, it was a triumph. The Quonset hut was cheaper to produce, faster to manufacture, easier to transport, and more versatile than the Nissen hut. Military planners celebrated the design as an example of American engineering superiority, taking a foreign concept and perfecting it through industrial know-how. Production ramped up to astonishing levels. At peak output, American factories were completing one Quonset hut every 15 minutes, 24 hours a day. But something had been lost in the translation from battlefield engineering to industrial production. The changes that made the Quonset hut easier to manufacture had fundamentally altered its structural physics. And those alterations wouldn't become apparent until the structures faced the same test that had proven the Nissen hut's genius: combat. The segmented arch design created stress concentration points that didn't exist in the Nissen hut's continuous curve. Each joint where arch segments connected became a potential failure point. When a blast wave struck a Nissen hut, the force distributed smoothly along the entire curve. When it struck a Quonset hut, the force concentrated at the joints between segments. The welded or bolted connections at these joints were rigid. They couldn't flex or absorb energy. They either held or they failed, with no middle ground. Understanding why requires examining how joints behave under dynamic loading. In a continuous structure, forces flow smoothly from one section to the next without interruption. In a segmented structure, forces must transfer through discrete connection points. These connections become stress concentrators, locations where force intensity increases dramatically. It's like water flowing through a pipe. In a smooth pipe, water flows evenly. At a joint or fitting, turbulence and pressure spikes occur. The Quonset hut's arch segments were connected by bolted or welded flanges, flat plates at the end of each segment that joined to the next segment's flange. When blast pressure pushed on the structure, these flanges had to transfer enormous forces from one segment to the next. The connection was rigid, meaning it couldn't deform to spread the load. Either the bolts held or they sheared off. Either the welds held or they cracked. There was no gradual failure mode, no ability to absorb energy through controlled deformation. In contrast, the Nissen hut's continuous curve had no such joints. The corrugated steel sheets overlapped and bolted to continuous wooden ribs that ran the full length of the structure. Forces flowed smoothly along these ribs without encountering discrete connection points. The overlapping sheets could slide slightly relative to each, distributing loads and accommodating movement. The structure could deform locally without triggering cascading failure. The heavier steel gauge compounded the problem. The Nissen hut's thin steel could flex slightly under pressure, acting like a spring to absorb and dissipate energy. The Quonset hut's thicker steel was more rigid. It didn't bend, it cracked. When blast pressure exceeded the steel's yield strength, it failed catastrophically rather than deform and recovering. The improvement in material thickness had actually reduced the structure's resilience. This reveals a fundamental misunderstanding about material behavior under extreme loading. In static conditions, normal use without explosions or impacts, Thicker material is indeed stronger. It can support more weight, resist more pressure, and last longer under normal wear. But under dynamic shock loading, the relationship between thickness and survival is more complex. A material that's too rigid can't absorb energy through deformation, so all that energy goes into creating damage. A thinner, more flexible material can bend, absorb energy, and return to its original shape, surviving through resilience rather than resistance. The integrated floor created a third vulnerability. The Nissen hut's separate floor meant that ground shock from nearby explosions was partially isolated from the walls. The floor could move independently, absorbing some of the vibration without transmitting it to the structure. The Quonset hut's attached floor acted as a diaphragm, transferring ground vibrations directly into the steel frame. Worse, the floor could catch blast waves from below. Explosions create pressure waves that travel through the ground as well as the air, and transmit that force upward into the structure's weakest points, those segmented arch joints. Structural engineers call this coupling, when different parts of a structure are rigidly connected so that forces in one part directly affect other parts. Sometimes coupling is desirable, allowing different elements to work together. But under blast loading, coupling can be catastrophic, allowing shock waves to propagate through the entire structure instead of being isolated and dissipated locally. These weren't theoretical concerns, they were documented in the field. In the Pacific Theater, where Japanese air raids targeted American bases throughout 1943 and 1940, engineering reports began noting a pattern. Quonset huts near bomb impacts showed panel separation at the welded joints. The arch segments would pull apart, creating gaps that compromised the entire structure. In some cases, entire sections of the roof would peel away, leaving the interior exposed. The contrast with British structures was striking. In Burma, where British and American forces operated side by side, older Nissen huts from earlier campaigns survived bombardments better than newly constructed Quonset huts. A U.S. Army Corps of Engineers report from 1944 noted, British semicircular shelters demonstrate superior blast resistance compared to domestic Quonset-type structures of similar dimensions. Failure mode analysis suggests joint rigidity in domestic design creates stress concentration absent in British continuous curve construction. The report was buried in military archives, classified not for security reasons, but because it was embarrassing. America had produced nearly twice as many prefab shelters as Britain, had done so faster and cheaper, had employed cutting-edge industrial techniques, and had somehow created an inferior product. The Quonset hut wasn't a failure by any reasonable standard. It served admirably in protected rear areas, housed millions of servicemen, and became an icon of American military logistics. But in direct combat conditions, under the specific circumstances that the Nissen hut had been designed to survive, the American redesign fell short. The irony was profound. American engineers had looked at the Nissen hut and seen a primitive design that needed modernization. They saw inefficient manufacturing, non-standard components, and old-fashioned construction methods. What they didn't see, what they couldn't see without understanding the underlying physics, was that every inefficiency in the Nissen hut served a purpose. The continuous curve wasn't difficult to manufacture by accident. It was difficult because that specific geometry was essential to the design's performance. The thin steel wasn't a cost-cutting measure, it was a carefully calculated choice that flexibility. The separate floor wasn't a construction shortcut. It was deliberate isolation of different structural elements. Peter Nissen had designed his hut in the field, under fire, with the immediate feedback of combat conditions. Every aspect of the design had been tested against the most demanding criteria imaginable: survival under artillery bombardment. The American engineers designed their hut in offices and factories, optimizing for production metrics and cost efficiency. They tested prototypes against engineering specifications and manufacturing tolerances, but they never tested against the one thing that mattered most: the brutal, chaotic physics of high explosives. This wasn't a failure of intelligence or competence. American engineers in the 1940s were among the best in the world. They had designed the B-29 Superfortress, the most advanced aircraft of the war. They had built the atomic bomb. They had created radar systems, proximity fuses, and countless other technological marvels. The problem wasn't capability, it was perspective. The Nissen hut emerged from a tradition of engineering that prioritized function over form, survival over efficiency, battlefield performance over production metrics. It was designed by a man who had spent years underground, where the consequences of structural failure were immediate and fatal. The curve wasn't an aesthetic choice or a manufacturing convenience. It was the distilled essence of what Nissen had learned about how materials behave under extreme stress. The Quonset hut emerged from a tradition of industrial engineering that prioritized standardization, interchangeability, and mass production. It was designed by teams who had spent years optimizing factory output, where success was measured in units per hour and cost per unit. The segmented arches and standardized panels weren't mistakes. They were logical solutions to manufacturing challenges, but they were solutions to the wrong problem. This distinction reveals something fundamental about engineering itself. True engineering isn't just about making things. It's about understanding why things work before you try to improve them. The Quonset hut's designers copied the Nissen hut's form, but missed its function. They replicated the semicircular shape without grasping why that shape mattered. They saw a curved steel building and thought they could make it better by applying industrial production techniques. They didn't realize was that the curve itself was the innovation, and everything else, the materials, the assembly method, the specifications, flowed from that central insight. In the decades after World War II, both structures found civilian lives. Quonset huts became ubiquitous across America, used as storage buildings, garages, workshops, and even homes. Their standardized design made them cheap and readily available as military surplus, but their lifespan proved shorter than expected. The welded joints corroded faster than the panels themselves. The rigid connections failed under repeated thermal expansion and contraction. By the 1970s, most Quonset huts from the war years had been demolished or abandoned, their steel frames rusting and collapsing. The Nissen huts, meanwhile, endured. Across Britain and former British territories, structures built during World War I continued functioning into the 21st century. Some have been maintained and restored, protected as historical structures. Others simply persist through benign neglect, their curves still perfect, their corrugated steel still sound after more than 100 years. The difference in longevity isn't accidental. It's the inevitable result of design philosophy. One structure was built to be produced efficiently. The other was built to survive indefinitely. The lesson extends beyond military architecture. In every field of engineering, there's a constant tension between optimization and understanding. Modern industrial processes excel at making things cheaper, faster, and more standardized. But optimization assumes you understand what you're optimizing. If you don't grasp why something works, your improvements might actually be degradations. Consider the Nissen hut's curve one more time. That semicircular cross-section wasn't chosen because it looked good or because it was easy to describe mathematically. It was chosen because Peter Nissen understood, at a deep intuitive level, informed by years of mining engineering, that a curve distributes force evenly. He understood that flexibility absorbs shock better than rigidity. He understood that simplicity in design enables reliability in the field. Every decision in the Nissen hut's design flowed from these fundamental insights about physics and materials. The Quonset hut's designers understood manufacturing. They understood logistics and standardization and industrial production. These are valuable forms of knowledge, essential to modern civilization. But they're not the same as understanding structural physics under combat conditions. And when you optimize for one without understanding the other, you get a structure that's easier to build but harder to keep standing when explosives start detonating nearby. This isn't a story about American failure or British superiority. Both nations produced remarkable engineering achievements during their respective wars. The Quonset hut, despite its limitations compared to the Nissen hut, was still an impressive accomplishment that served its purpose well in most circumstances. The point isn't that American engineers were incompetent. They demonstrably weren't. The point is that copying without comprehension leads to subtle degradations that might not be apparent until conditions become extreme. The heart of the Nissen hut, the thing that made it truly revolutionary, wasn't the steel or the corrugations or even the speed of assembly. It was the understanding that survival under extreme conditions requires designs that work with physics rather than against it. The curve wasn't decoration, the flexibility wasn't weakness, the simplicity wasn't primitive. Every aspect of the design was a conscious choice based on deep understanding of how materials and forces interact. When American engineers redesigned the Nissen hut, they kept the superficial elements, the semicircular shape, the corrugated steel, the prefabricated construction, but lost the underlying wisdom. They made it more manufacturable but less resilient. They optimized for production but de-optimized for survival. They improved everything except the one thing that mattered most. Today, if you drive through the English countryside, you might pass a weathered steel structure with a distinctive curved roof, still serving as a barn or storage building a century after its construction. That's a Nissen hut, still standing, still functional, still demonstrating the genius of its design. If you drive through rural America, you might see the rusted remains of a Quonset hut, its panels separate, its frame collapsing, abandoned after a few decades of use. The difference between these two structures, one enduring, one decaying, is the difference between engineering that understands its purpose and engineering that optimizes its process. It's the difference between designing for survival and designing for production. It's the difference between copying a form and comprehending a function. Peter Nissen drew a curve on paper in 1916 and changed military architecture forever. American engineers copied that curve in 1941 and thought they had improved it. But you can't improve what you don't understand. The Nissen hut's genius wasn't in its components, or its assembly method, or its cost efficiency. It was in the deep understanding of physics that informed every design decision. That understanding, that wisdom about how forces move through materials, how curves distribute pressure, how flexibility enables survival, was the heart of the innovation. America's redesign lost that heart. They kept the body, the outward form, but removed the animating principle that made it work. The Quonset hut was a corpse of the Nissen hut, similar in appearance, but missing the essential spark of life. And in engineering, as in biology, a body without a heart cannot survive for long. The story of these two structures is ultimately a story about the nature of innovation itself. True innovation isn't about making things bigger or faster or cheaper. It's about understanding problems so deeply that solutions emerge naturally from that understanding. Peter Nissen didn't set out to design an iconic building. He set out to solve a specific problem: how to shelter soldiers under artillery fire. The Nissen hut was his answer, and it was perfect because it was born from complete understanding of the problem it needed to solve. The Quonset hut was born from a different question. How do we mass-produce shelters efficiently? That's a valid question, but it's not the same question. And when you answer a different question, you get a different solution, one that might look similar but performs differently when tested against the original problem. In the end, the Nissen hut survived blasts because it was designed to survive blasts. The Quonset hut was designed to be manufactured efficiently, and it succeeded at that goal admirably. But when the bombs started falling, when the artillery started firing, when the structures faced the test they were supposedly built for, the difference became clear. One had been forged in the crucible of combat engineering. The other had been optimized in the comfort of industrial planning. The curve that Peter Nissen drew in 1916 contained more wisdom than 1,000 factory optimization studies. That simple semicircle represented years of experience with pressure and materials, distilled into pure geometric truth. When American engineers straightened that curve into segmented arches, when they stiffened that flexible steel into rigid panels, when they integrated that isolated floor into a structural diaphragm, they thought they were making improvements. They were actually removing the very features that made the design work. This is the lesson that echoes across a century. Understand before you optimize, comprehend before you copy, and never mistake efficiency for effectiveness. The Nissen hut's heart was its curve, its flexibility, its deep understanding of survival physics. America's redesign lost that heart in pursuit of production metrics, and a structure without a heart, no matter how efficiently produced, cannot truly live. If you found this story of engineering wisdom versus industrial efficiency fascinating, make sure to subscribe to the channel so you don't miss our next deep dive into history's forgotten lessons. Hit that like button if you appreciate content that goes beyond the surface to uncover the real reasons why things succeed or fail. And drop a comment below. I'd love to hear your thoughts. Do you think modern engineering sometimes loses sight of the fundamentals in pursuit of efficiency? What other historical designs do you think were improved but actually lost their genius? Your insights make this community richer, so share your perspective. Thanks for watching, and I'll see you in the next one.